Okay, thank you. Is this on? Can people hear me? Okay, good. So first let me thank the organizers for inviting me and for the Newton Institute for inviting all of us. It's always a pleasure to come back to Cambridge. So today I want to tell you about a project that I've been working on for a number of years. I think some of you here have seen a lot, probably not all, of what I'm going to talk about today. But since I expected this to be a somewhat broader audience, I'll try to give you a fairly coherent description of the work that me and some of my collaborators, and in particular Bella Szilagyi, Nick Taylor, Oliver Rene, have been doing for a number of years. And that is trying to develop a framework in which would allow us to solve various kinds of partial differential equations on manifolds with arbitrary spatial topology. So in particular, I'm rooted in 4 dimensions. I'm not up to 13 yet, so I'm thinking about sort of one time dimension and a arbitrary spatial topology. So the first thing you can ask, well, if you really want arbitrary topologies, why don't you go to arbitrary space-time topologies? And it turns out that 4 manifolds are unbelievably more nasty even than 3 manifolds, which were already fairly complicated and nasty. I'll say another comment about why I think it's probably impossible ever to try to write a code to do things on really arbitrary 4 manifolds in a minute. And this particular format, that is something which is R cross some 3 manifold sigma, is an interesting set of problems from a physics point of view. So you can imagine setting initial data for some evolution type PDE system on this spatial manifold. You want to evolve it in time. And then this is the topological structure of the Cauchy development of the initial data. So that's why I'm interested in manifolds with that structure. Why I'm interested in topology at all, you can ask, is a reasonable question that probably should be answered by psychologists rather than mathematicians. So I guess I've always been curious about topology. And Einstein's equations tell you how to compute the geometry of a particular manifold, if you know what the matter inside of it is, but it doesn't tell you which manifold to use. And in particular, it doesn't tell you which topology of the manifold to use. So in principle, you can have solutions on all kinds of strange manifolds. There's a little bit of work, both analytical work historically and a little bit of work numerically, that has explored solutions on these different topologies. But it turns out there are some fundamental blocks that prevent a standard numerical relativity code from being transported over and used to do something on a more complicated topology. So we wanted to learn how to solve those fundamental blocks that would keep us from using our standard codes. So in some sense, what I'm talking about doesn't quite fit into the structure preservation and general relativity. It's not really structure preservation. It's not really general relativity. It's something that's more fundamental than either of those, and it's just how do you set up the problem of solving PDEs on complicated manifolds like this. Okay, so let me first tell you what I mean by an arbitrary 3 manifold. So there are some theorems that tell you that any 2 or 3-dimensional manifold admits a triangulation. That is, it can be represented by a sum of triangles or tetrahedra in 3 dimensions, plus a set of rules for gluing the faces of those simplices together. In 4 dimensions, that's apparently false. Apparently, there exist 4 manifolds that do not admit triangulations. And so I think if you can see that, I think it's clear nobody is ever going to do numerical anything on those kinds of manifolds. So we're going to stick with 3 manifolds, and we're going to characterize them in this way. For 2 manifolds, we, of course, completely understand how to build all of the topologies. Things are characterized by their genus numbers. That is, if you take a 2-sphere and you sort of add handles to it, the genus number just counts the number of handles. And once you specify that, that specifies the topology of all of the orientable compact 2 manifolds. In 3 manifolds, there's no such classification. We know there's an infinite number. I'm not sure whether it's even known whether it's countable infinite number. It's a large number. There are lots of catalogs of huge numbers of these things. So in some sense, you know, in the 19th century, they said there's two kinds of science, physics and stamp collecting. So this is sort of in the stamp collecting phase of this branch of mathematics. You can write down lots of examples. And there are some theorems. The Thurston geometrization theorem says that you can write every 3 manifold as a direct sum of things called prime manifolds. And these prime manifolds have the property that they admit a unique uniform geometrization. And it turns out there's 8 different classes of these things. But that doesn't help you much in sort of constructing all of them. It just is a way, if you've got one, you can figure out which class it belongs to. But it doesn't tell you how to construct more of them particularly. Okay, so there's lots of 3 manifolds. So how are we going to get access to them? So it turns out that there are catalogs. And one of the convenient ways to find one of these catalogs, there's this wonderful software tool called Regina or Regina, I don't know how you pronounce this, which is it's a tool for creating, manipulating, and visualizing manifolds that you can construct with triangulations in low dimensions, 2 and 3 dimensions, and I think they're working on 4. This thing was developed by some mathematicians, Benjamin Burton, Ryan Budley, and William Peterson. This is just some screenshots. This just shows you sort of what the name of the software is and where you can download it. It's free. It operates on all kinds of platforms. And these are just the authors of this. Now, from my perspective, one of the useful things, if you download this, you can go to a place which is a catalog of 3 manifolds. And so what they've done, I know that this is basically invisible, just this is supposed to represent a long list and the individual entries are not so important. They start up here, they take one tetrahedra and they hook it together in all possible ways. It turns out you can build 3 different orientable manifolds in that way. So there are 3 things you can compose with one tetrahedra. There's a longer list with 2, 3, 4, 5. This is all the ones you can construct from 6. This is all the ones from 7, and that's all that would fit on one slide. So in the software that you download, they've got all of them up to 10, and I think there's something like 10,000 of these things. They've also done 11 and maybe 12 at this point, and you can download them, but the files are so big they don't include it in the package. So the point is we have access to lots of structure information about what 3 manifolds look like. So each of these things, if you click on one of these in the software, you can generate a whole bunch of pages that allow you to do various things. So this page, which is particularly interesting to me, is the definition of the connection of the different faces of the tetrahedra. So each tetrahedra, they have vertices labeled 0, 1, 2, 3. And so this table says if you take tetrahedron 0 here, that the 0, 1, 2 face of that should be connected to the 2, 3, 1 face of tetrahedron 4, et cetera. So this table tells you everything you need to know about how to connect these guys together. So that defines the manifold. So that's one of the things that's built into this. And then they have a bunch of pages that give you various properties of this. So for example, when you connect all of these things together, it turns out there's only one vertex. All of the vertices get identified. There are 7 edges which are independent, and 12 independent faces, and 6 tetrahedra. There are other pages. This is a little diagram. Sort of each of these dots represents one of the tetrahedra, and the line represents a connected face to this tetrahedra, so it just shows you how things are connected up. There are other pages that show you various properties of these things. For example, this is something they call it irreducible. That's whether it's a prime submanifold, which is one of the things that the Thurston theorem tells you. This particular 3 manifold that I chose for this example, its name is some complicated thing up there. It happens to live in the Thurston class nil. So it accepts one of the those geometries. Okay. So all of these things are compact. Okay? So I can create any boundary you like. I can just take a tetrahedron out, okay, and that'll be sort of this thing with an outer two-sphere on it, for example. And there's other ways you can remove things to create boundaries.
So the ones in the catalog
the ones in this catalog, so the catalog I show you are the compact orientable ones. They have another catalog that's almost as long for the compact non-orientable ones, but for physics points of view, having the orientable ones are most interesting. You can't build spinor structures on things which are non-orientable, so we've stuck to those. Okay, so our goal is to develop numerical methods that allow us to sort of easily use any of this information and solve PDEs on them. So how do we do that? So for various reasons, cubes make it easier to find something about differential structure that I'll talk about in a minute. I think you could do it directly with the tetrahedron representation, but it's the algebra is somewhat easier if you do it with cubes. And also, various numerical methods like spectral methods and finite difference methods really would like to have computational domains that are cubes rather than tetrahedra. Finite element methods may prefer to stick with the tetrahedra-based things, and that's okay with me, but we're going to analyze things with cubes. So the question is, if I start off with one of these triangulations, how can I turn it into something made out of cubes? And it turns out that's easy. It turns out every 2- and 3-dimensional triangulation is probably true in n dimensions, but I haven't actually worked out the proof. You can refine it into what I call a multi-cube representation. So here's how you do it. You take one of the tetrahedra and you add in more vertices at the midpoints of each of the edges. And then you add in a second set of vertices at the centroids of each of the faces, and then you connect these centroid guys up with the midpoint guys with extra edges. And then you add one more in the middle at the centroid of the entire tetrahedra, plus the extra edges, plus the extra little faces that got determined by this. And that basically has cut this one tetrahedra into 4 cubes, or topological cubes. I've shaded the ones around those vertices so you can more clearly see the cubic structure around A and B. So given any triangulation, you can easily rewrite it as a set of cubes which are glued together at their faces. Okay? You can also build things out of cubes which don't come from triangulations, but since we know everything has a triangulation, you can always get one by doing this. So in a more abstract point of view, we decided that the way we wanted to construct our numerical method was to base it on this series of cubes or blocks. So we have some set of cubic regions. This B sub A represents this list of blocks that it takes to glue together to form the structure of the manifold. And then you also need some maps that tell how to take the boundaries of one of the blocks into the boundaries of another block. So this notation says this is the beta boundary, tells you which face of the block B, and then there's some map that maps that boundary face into the boundary face of its neighbor and gives you that face. So you have to somehow specify what those maps are in order to build this structure. Here is a little example. The standard sort of cubic, it's called a cube sphere or something like that, representative of a two-sphere. So these colored regions represent various blocks. Here I've cut them out as squares and laid them down next to each other. And then the 2 blocks that are next to each other, say along that interface, I've located them in this 2-dimensional plane right next to each other. And then these extra faces, so for example, this face gets identified with that one and this one with that one, et cetera. So there's some list of rules for how you have to construct these things. If you take your blocks, and we're just dealing with topology, so size doesn't matter, but for convenience in the computer, we choose all of the regions to have this uniform size and orientation. Okay, so you take the coordinates inside of each blocks, and you have them all the same size. When you do that, it's easy to construct convenient maps. So say in our mapping we're supposed to map this face onto this face of that cube. So we need to tell the computer exactly what this map is. So one way to do that is with a simple linear transformation like that. And what this is saying, these are the coordinates of points on this beta face of this B block. This represents the center point of that block, okay? And so when x equals c, this is 0, and so it says that that maps the center of this block to the center of that block. And the c is some rotation reflection matrix that tells you how to orient this square into the right orientation so that it hooks onto that in the appropriate way. And there's a finite number of these. I think there's only 48 possible rotations of squares into squares. And so it's easy to tell the computer sort of all possible maps of this sort. And when you specify in the computer sort of which manifold am I using, you have to give it this list of domains. You have to tell it where you're going to place them in your coordinate space of this Rn that you're putting them in. And that then determines where the centers of all of the faces are. And then for each of the boundary maps, sort of each of these guys, you have to tell it which is the appropriate rotation matrix to get these to line up properly. And so that can all be sort of fed into your code with one input file that's done sort of very easily. And then that fixes that structure for that manifold once and for all. Now, Oliver Rinne, who is, he's now in Berlin, but he was a postdoc of mine at Caltech, has worked on me over the years with this. He's developed a nice little Python code that can take the output from this Regina triangulation package, which gives you the tetrahedra gluing matrix that I showed you from the output. You can output that as a little file from Regina. And it inputs that file, and then it automatically constructs this multi-cube structure. It tells you which cubes to use, it tells you where to place them, tells you which rotation matrices you need to use in order to get all of this to hook up properly. So let me show you a visualization of an example. This is actually the same example that I showed you in those page images. So this is it's something called a Seifert fiber space. It's some fiber bundle type construction. That's the base manifold. This tells you something about how the fibers are twisted. It's composed of 6 tetrahedra. So each of the tetrahedra we sort of do sort of separately and locate it as a place. And then by that construction I showed you, each tetrahedra is cut up into 4 cubes. And so there are the 4 cubes that represent each of the tetrahedra. And then his code also tells you sort of exactly, it'll tell you, I don't remember how this is done, but say that square is connected to this guy. I don't remember if that's actually the right number, but it'll tell you that that is the connection and which rotation matrix you need to use to get it to line up with the right orientation. So we've constructed a whole bunch of these. In fact, our sort of goal for the next paper is to have a couple examples from each of the Thurston classes, just to show that we can do lots of different things. You can also construct things sort of manually, just like the cube sphere representation of a 2-sphere is a nice cubic representation, but it doesn't actually come from one of these triangulations cut up. It's something that's done sort of on the side. And some of these manifolds, so there are a bunch of famous 3 manifolds. There's one called Seifert-Weber space, which is a hyperbolic 3 manifold that's built from dodecahedron by identifying opposite polygonal, or I think they're 5-sided faces rotated in the right way. Anyway, by hand, we constructed a 20-cube representation of that. And this is the multi-cube representation we built out of that, whereas I think the minimum triangulation available for that also has something like 20 tetrahedra. So if we use the standard construction, we would have ended up with something with 80 cubes instead of 20 cubes. So this is, in some sense, more efficient way to represent these things. Okay, so this is what I mean by arbitrary. Okay, so we can do lots of things, and the goal is to be able to have the code, so I don't have to think about this. When some mathematician or string theorist or somebody says, we really want to know something about this particular manifold, I don't have to spend 3 years trying to figure out how to code it up. We just sort of create the input file, and then the code just does things. Okay, so that's the first step. The second and much more difficult step has to do with this differentiable structure. So these maps that glue these boundary faces together make sure that the continuity of things is right, but it doesn't guarantee that things will be differentiable in an obvious way across those boundaries. And let me just go back a minute and show you this picture again of the two-sphere. Okay, these extra curves on here are actually the curves of constant angles, you know, the theta and phi, the standard coordinates on a two-sphere. So this is the North Pole, where all of the different phi directions, and this is the South Pole of this. So these lines that radiate out are constant phi surfaces, and then they go into these vertical lines in this middle bunch. And the constant theta surfaces are circles, and in these domains they look like circles, but when you get down here they look like this sort of lacy thing, and then that's the equator of this two-sphere. So you can see that even though theta is a nice smooth function, except at phi equals 0, it has a kink when you go across this boundary. So if you just glued things together in the obvious way and says, okay, well, when you go from this domain to this, if you have a vector, then, you know, if the components are the same on this side and this side, then it's a continuous vector. That would be wrong, okay? That gives you the wrong differentiable structure. So the question is, how do you do it properly? So here's another picture of this same thing where I've taken these 3 blocks, and since the space locally around this vertex point is flat, I can take those blocks and I can sort of put them down in a flat plane, and I want there to be no conical singularity there, so I have to distort the shape of these in order to make sure that you get 2 pi when you go around the circle. And so that means if you look at sort of the normal, quote, normal vector in coordinate terms along this direction, it's a vector that looks like that, but the analogous one on this side looks like that. So if you tried to take a vector which you're representing as components with respect to these coordinate basis functions, the components of a continuous vector will not be continuous as you go across this interface. Okay? So somehow you have to tell the structure how to do this properly, how to put the right kind of discontinuity in there so that it actually represents a continuous vector field. And the thing that does that is something called a differentiable structure. So if you look in the standard textbooks about constructing differentiable structure on manifolds, what they tell you is you should never do what we're doing here, which is you're not supposed to have coordinate systems that just touch along an interface. You're supposed to make them overlap. So here is our two-sphere. So they tell you you're supposed to choose some other set of domains, these Ds, that are bigger. So here is this green block, and here is a bigger guy, and here is the neighboring guy with a bigger red one that goes around it. They're supposed to overlap, and then you build a differentiable structure by making sure that the interface, the transition functions between this coordinate system and that coordinate system are smooth, or C2, or whatever degree of smoothness you want. So in principle, if we could figure out how to do this in an automatic way, I would be ecstatic. And if anybody out there knows how to do it or can figure out how to do it, please let me know, and we'll do this. But we couldn't figure out how to do it in a sort of completely automatic way that would just flow from the simplex structure. So we decided, okay, well, what do we really need? What's the bare minimum that we can get away with? And we realized that all you really needed was some set of Jacobians. And so here are some Jacobians. and they have lots of indices. What do the indices mean? So this is a Jacobian that tells you how to transfer something from the beta face of block B to the alpha face of block A. And here is how you would use it. So if you had a vector on this boundary in the B domain, and you wanted to know what it would look like if you transformed it properly over into the A domain space, you just multiply by this Jacobian. If you actually had these overlap maps of coordinates in the natural way, these Jacobians would just be the partial derivatives of one coordinate system with respect to the other, but we don't have that, so it's just some abstract thing that tells you how to do this mapping. And the notation I use, these brackets mean do the transformations to go from this B object into the A block representation. And you have a dual Jacobian that tells you how to do it for dual vectors. Okay? You can define, so if you have these Jacobians, then you can define what it means by vector and tensor fields to be continuous. Basically, if you take one of these B guys, transform it with the Jacobians, and you get the vector you had on the A side, then that vector field would be continuous. And similarly for covectors. Okay, but that's still not quite what you need. You would also like to know not only whether the vectors are continuous, but you would like to know whether they're differentiable, right? If you're going to solve some, like Maxwell's equations or Einstein's equations, you want to know not only that the fields are continuous across the boundaries, you would like to know that they're differentiable at some appropriate level as well. So how do you do that? Okay, well, the minimum thing we could think of, if you had a covariant derivative somehow, God gave it to you, which was determined by some smooth connection, who knows how you get this thing, then you can define differentiability of tensors across these interfaces simply by taking the gradients of vector fields. And so this is now a second-rank tensor. And you use one Jacobian for each index, transform it into the guy next door, and if they're the same, then it's differentiable, and similarly for covectors. So if you had this covariant derivative, you could do that. So really, if we're going to do PDEs, we need both things. We need to know how to compute a set of Jacobians that tell you how to do it, and we're going to need to know how to build a covariant derivative. How do you do that in an efficient way? So one thing we realized that if you had a metric, a smooth metric, that would be enough. Okay? So certainly if you had a smooth metric, that determines a covariant derivative that you could use to define the continuity of gradients. And it turns out the metric is also all you need to define these Jacobians as well. And I'll show you on the next slide how to do that. So let's assume we have one of these smooth metrics, and we're going to represent it in block A like this, and in its neighboring block B like that. And we're going to use this reference metric to define a set of outward-directed unit normal vectors. Okay, so so this is the unit normal vector on this A block, and the I down index means it's a covector. So it's easy to construct that, right? You just take the gradient of a function which is constant on the boundary, and then you use the metric to normalize it. So you just change the overall scale of it, and that makes this, these down index vectors. And the up index vectors, you just take the inverse of these guys and raise the index. Okay, so that's how you build the normal vectors. Just depends on the metric. And by the way, I said that in some sense, building this differentiable structure on cubes is easier than tetrahedra. In the cubes, you can always arrange it so the coordinates are constant on the boundaries. And so the formulas for these normal vectors is particularly simple there. You could do it with tetrahedra, but it's more complicated because you're going to have to use some coordinate system in some way, and then there's going to be some formulas. You can do it, but it's just more baggage. So given these normal vectors, then it turns out there are just some formulas for these Jacobians. Okay, the formulas depend on these normal vectors, and they also depend on these rotation matrices from the maps that told you how to map one boundary onto the next. Okay, so how do I know that these are the right formulas? So you can test them So for example, if you take the Jacobian and you dot one of the normal vectors into it, you should get the normal vector on the other side if it's continuous. And in fact, this formula has that property. There's a minus sign because these were both outward directed normal vectors, and so if this one is outward directed in B, then it's inward directed in A, and so you need a minus sign. Similar formula for the dual Jacobian. If you have a vector which is tangent to the boundary, then what these Jacobians do, it just tells you to rotate it using this map that you use to connect the boundaries together. And that's exactly what you would expect it to do. And finally, you can contract the Jacobian into the dual Jacobian, and it turns out they're inverses. And that's just exactly what you would expect if you use the standard overlap formula. So these are exactly the formulas you need. If you have this reference metric, you're in good shape. You've got everything you need. Okay, so how do you get the reference metric? So when we first started doing this, we started doing simple manifolds, S3, S2 cross S1, things like that. And in those cases, you can just analytically write down a reference metric because you know a nice metric on that thing, and you just do the transformation into your multi-cube representation. But for arbitrary manifolds, this isn't going to work. In 2 dimensions, we know how to solve this exactly. In 3 dimensions, we know how to solve part of it exactly. So I'll tell you what we can do and what we don't know how to do so far. So for arbitrary 2 manifolds, you can do things as follows. So you look at each vertex that you get in this multi-cube representation. So here is a vertex, and here are a bunch of, in 2 dimensions, squares that surround that point. You want to make sure that whatever metric you've got, that there's no conical singularity hiding at that vertex point. And so we should be able to put a metric on a sort of a little patch around that point, which is flat. So in particular, I'm going to take, I've drawn 5 of these things, but it can be any number depending on what the representation is. And I'm going to put a metric on this so I have a flat metric everywhere on this sort of star-shaped domain that surrounds this vertex point. And the way I can get the code to do that is I just have the code go around and figure out how many cubes there are associated with that point, and I define an angle, which is 2 pi over n, that I'm going to use as the opening angle around for each of those. And then I just write down analytically what a flat metric looks like in coordinates which have been skewed by that opening angle. Okay, so our code does that automatically. You have to build one of these flat metrics for the domain around each of these points. And they won't all agree, otherwise the manifold would be flat, and we know that's wrong. So what you have to do is average these flat metrics in some appropriate way. And what you do is you build a partition of unity. That is a function which is 1 around the point where we want the metric to really be flat and have no cone singularity, to fall to 0 at the edge of this star-shaped domain around that point. And if you add up these partition of unity functions from all of the other domains that would intersect at this point, it always adds to 1. Okay? And then you just take the flat metrics that you get from each of those star-shaped domains, multiply it by this partition of unity function, add them all up. That gives you a nice positive definite metric, which is continuous. It has no conical singularities because you've sort of made sure that they don't exist anywhere. And that works fine. So that gives you a metric which is continuous everywhere. It doesn't have singularities at the bad points, but it turns out it's still not differentiable across the boundary. So I'll talk in a minute about how to fix that. In 3 dimensions, we can also do this. There are 2 places you can end up with conical singularities. One is along edges. So in the middle of this is an edge. It's like you take one of these and then extend it into blocks in the z direction. And so we do basically the same thing as we did in the 2-dimensional case. You build a flat metric. You sort of add up the number of blocks, build that angle, and that gives you a flat metric in that domain. So that's sort of an edge-type domain. And similarly, you can have points around vertices, and so you get a bunch of cubes that sort of pack in around that vertex. And to build the flat metric in these guys, you have to determine what these angles are between the tangent vectors to the edges of the boundary, but that can all be done easily, automatically by the code. It just goes around and figures out how things are connected together, adds up how many guys there are, and it does that geometry for you. So it's straightforward. We can compute these C0 metrics by averaging these flat metrics around each of the possible danger points where you might have conical type singularities hiding. Okay, but we really need a little more differentiability. C1 turns out to be good enough, but I'll talk about a bit about how to go more beyond that. So in general, so randomly. Okay, so we tried various things. We just took we built it out of simple polynomial type things that would be 1 at one boundary point and fall to 0 as fast as we like at the other boundary point. And we just tried several things to see which ones the code had an easier time resolving, because we didn't want to sort of waste resolution on this reference metric whenever possible. There may be some clever way to do it, and if you know what it is, please come and tell us, because... Pardon? So it's so there's C infinity in each block, but across the surfaces of the blocks, they're less differentiable. Okay, they're continuous, but in general, they're not differentiable.
You're trying to construct a metric which is C1 on its manifold.
Yep.
You haven't yet defined C1, but you use a metric to find what it means in C1.
Yes. So I'll tell you. So there's something called Israel's theorem. Okay, so Israel's theorem tells you that if you have two manifolds that meet at a submanifold, that the metric is C1 across the boundary if the extrinsic curvatures calculated from either side agree. So continuity of the extrinsic curvature is the necessary and sufficient condition for C1. Okay? So the strategy here is we're going to take this bar metric, which is the C0 piece, and we're going to add something to it. Okay? And this something is going to vanish on the boundaries, because I don't want to mess up the continuity and all that kind of stuff. But I want to adjust the derivatives of this thing so that the extrinsic curvatures are continuous across the boundary. And you can just work out a formula. This is the formula. So this is the derivative of this delta G guy that I'm adding to it in the direction of the coordinate, which is constant on the boundary. So this is the alpha coordinate on the alpha boundary. And then these are projection operators that take you into things which are tangent to the boundary. And there's a formula that says set that equal to the extrinsic curvature computed with the C0 metric on this piece and the one from the beta block next door transformed using the Jacobian guys that you're supposed to transform components of tensors. And the extrinsic curvatures are both defined with respect to outgoing guys, so they really should be equal to minus each other if things were continuous. So if the sum of these things was 0, then this would tell you just take delta G to be 0. You're done. But if it's not 0, if you add this piece, then you can show that the extrinsic curvature of this guy computed from both sides is in fact continuous. So that's the strategy. In 2 dimensions, we can do this, and it works numerically. In 3 dimensions, it doesn't. And I don't think it's fundamental. I think this is the right formula. But the way we've tried to implement this numerically in the code fails to work, is all I can say. And anyway, we're working on it. So that's where we are at the moment in 3 dimensions. We want to choose what this delta G is. We don't care what it is. We want it to be something which is smooth enough in the interior that it doesn't mess things up. We want it small enough so that it doesn't make this metric singular. But other than that, we just don't care. All that we care is that the boundary, it stays 0, and the derivatives satisfy that conditions, and we're done. So how to do that in a nice way, we haven't figured out. Okay, and then this just says that that gives you continuous extrinsic curvature, and then Israel tells you you're done. If you want more differentiability than that, I can give that to you as well. You can use Ricci flow. Ricci flow is a parabolic equation for the evolution of metrics. And it has the property that if you start off with initial data that is, it doesn't quite have to be C2, it wants to be sort of C1 and only finite discontinuities in the first derivative. So if you start off with initial data that is sort of C2 minus, sort of almost C2, which is what our metrics are, and then you Ricci flow it, this is the Ricci flow equation. Since it's a parabolic equation, after basically one time step, what you have is C infinity. Okay, so if you want to smooth things, you can just Ricci flow them for a while. I'll show you some examples. We did a bunch in 2 dimensions where we could actually set these things up properly. We did a bunch of Ricci flow. This is a particular example. It's a genus 5 thing, so it's a sphere with 5 handles off of it. These are one way to do a block structure of that genus 5 manifold. If you put on this C1 reference metric that we constructed analytically using our formulas, it's a mess. Okay, this is the scalar curvature. You can see it varies all over the place. But then, if you Ricci flow it, let's see, I hope to have a movie here. It just melts away. And we basically ran we ran it farther in the simulation, but then I'm running this the beginning of this backwards so you can see sort of more clearly what Ricci flow does. It basically takes any of these 2 manifolds we look at, and the theorems tell you that in those cases, any evolution by Ricci flow should produce a constant curvature metric, and we showed numerically to very high accuracy that this works. Okay, so let me move on and just say a little bit about, okay, so I've told you how to build these multi-cube structures. So here is an S2 cross S1 example. S3 looks something like that. The idea is to solve PDEs within each of these cubic regions using some standard code. Okay, we don't care how you do it. If you like finite difference or finite elements, it's okay with us. We use spectral methods in the code that my group developed. In order to get the right global solutions, you have to impose boundary conditions on all of these cube faces that are connected together in a way to enforce the appropriate continuity conditions for whatever kind of differential equation you're solving. Different equations will have different conditions. Einstein's equations, for example, can be written as a first-order symmetric hyperbolic system. And in that case, what you're supposed to do is set the set of fields which are called incoming characteristics, so I'll write them as U minus, that's some collection of fields. You're supposed to set as boundary data for those guys the outgoing characteristics from the neighboring domain. Okay, so the boundary conditions for this kind of equation would be take the outgoing characteristics from the B domain, transform them with the Jacobians across the boundary, and use that as the data for the incoming guys in A and vice versa. Okay? For an elliptic equation, you would want to enforce sort of continuity of the solution and its gradients, for example. So it depends on what equation you have. That's you have to set a set of boundary conditions. So that's the idea of this approach. So let me talk briefly about Einstein's equations. It turns out when we first tried to do this, we used our standard numerical relativity code, and we said, okay, we just sort of use these methods. The methods that we developed, and I showed you how to do, tell you how to transform tensors across boundaries. But the standard first-order symmetric hyperbolic representation of Einstein's equation is not covariant. Okay, you have all of these first-order fields that are things like the partial derivative of pieces of the metric with respect to the x coordinate. Okay, so that's not a tensor of any kind. And we figured, okay, well, we're smart. We know how to convert partial derivatives to covariant derivatives. We couldn't get the code to work. We worked for a long time. We finally says, okay, let's give up. Let's try to find a completely covariant symmetric hyperbolic representation. Turns out you can do that. This is the sort of standard formula for the Ricci tensor in terms of derivative psi is my representation of the space-time metric here. I think Franz wrote down this formula where if you have partial derivatives here, then this is like a wave operator, and then there are various pieces of Christoffel symbols squared. Here the Christoffel symbols are replaced by the differences between the Christoffel symbol for this guy and your reference metric guy. These are now covariant derivatives with respect to this reference metric. There's a curvature of the reference metric. Anyway, so it's some slightly different formula, but this formula can be decomposed and built into a first-order symmetric hyperbolic system in much the same way that the non-covariant thing does. As soon as we implemented that in the code, it worked, boom, right immediately. We used a covariant generalized harmonic gauge condition where basically this delta function is set equal to some gauge source function that you get to choose randomly. And the vacuum Einstein equations then look like this. So it's a nice hyperbolic thing. These are the Pretorius constraint damping terms that are necessary to make any of these things stable. But we evolved this and it works nice. So we wanted a test problem. The easiest thing we could think of at the time on a non-trivial topology manifold is something called the Einstein static universe. The metric is just this round sphere metric on a 3-sphere. If you write it out in these multi-cube coordinates, it's a little more complicated, but it's some simple thing. You can write it down. This metric solves Einstein's equations with a particular cosmological constant. It also has matter with density given by that and 0 pressure. So we decide, okay, let's evolve this numerically and see what happens, make sure that our code works. Well, the first problem is that pressureless matter on a computer, especially a spectral code, is a disaster, right? Because the dust starts crossing immediately. But then we realized that you can actually produce a stress energy tensor which has a density and no pressure as a certain state of a massive Klein-Gordon field, complex Klein-Gordon field. Okay, so a field where the scalar field is just constant and it has a phase that goes e to the I mass times t. Basically solves the equation. It only has a density and no pressure. So we figure, okay, if this thing drifts away a little bit, then we'll use the dynamics of the Klein-Gordon field. We know how to solve equations like that very well, and we'll see what we get. Okay, so we did that, and we evolved it, and it blows up. And then we learn, I guess we probably learned this in our first GR class. These things have been known to be unstable since 1930 by Eddington. There's an instability, but we said, okay, well, we can handle that. It turns out there's only like 2 modes which are unstable. So we built a filter into our code which detects these possibly unstable modes and puts in a strong damping factor. So it kills those modes, lets everything else go as normal. And with that, you can evolve for a long time. So then we said, okay, let's do something more interesting. Let's perturb it with some gravitational waves. So we're going to add a perturbation. These are tensor spherical harmonics on a 3-sphere. This represents a linear combination. The A's are amplitudes. They're normal modes. They go like e to the I omega t, where these omegas are the frequencies of these particular tensor modes. So if you construct a solution which is the Einstein static solution plus this guy, to linear order, these are a solution of the perturbation equations. The scalar field is just this constant times e to the I times the mass of the scalar field times t. We evolved that combined system for the particular run that I'll show you. We took some randomly chosen amplitudes. I think we took like 10 modes, 1 from each k, just to have some combination of thing. We visualize it. This is a 2-sphere which represents the equator of this three-sphere. And on this, I have visualized this function, the square of this amplitude of the perturbations. And we choose a very small amplitude, it's like 10 to the minus 6, so that the square terms, the quadratic terms, are going to be like 10 to the minus 12, which we're not going to see, thank you. And we evolved it. So let me show you a quick little movie of the evolution. Okay, so it does stuff. Notice you can't see any of the boundaries between, this slice goes through 6 of these blocks that make up the solution. I think 2 pi is the light travel time for something to go all the way around this universe. So this little movie went for time 10. So that's more than 1 light travel time. In fact, we evolved this for a lot longer. We evolved it out to t equals 1,000. And these curves show, so we computed a difference between this analytic, this first order perturbation solution, and the numerical solution that we got by solving the full nonlinear Einstein equations. So this is a curve for 1 resolution. I think this uses 10 spectral collocation points in each direction in each of the blocks. This is 12, 14, 16, et cetera. So you increase by 2 each time you go down. And you can see that the error is just constant. It, and it converges. This is below 10 to the minus 12 at the bottom here. This is the same thing for the scalar field. It shows you how accurately you're reproducing the analytical model for the scalar field. You can say, well, okay, fine, you did that, but you cheated. You put in this crazy non-physical damping force to keep the thing from blowing up. Are you really solving Einstein's equations at all? And the answer is, well, no, not really. But this is the norm of, you take all of the constraints of the Einstein system. There's a whole long list of them in this formulation. And we just take a norm, an L2 norm of all those components of all those constraints. And this is what it looks like, also converges exponentially. And this one shows you the magnitude of this extra force that we had to apply to these terms to damp out the unphysical modes. And those also converge away. Okay, so in some sense, we've shown that our code is stable. We've solved this slightly weird unphysical problem, but that's okay. We just wanted to know whether we were capable of doing anything like a hyperbolic system on this. Okay, so I'm about out of time. Let me just summarize. So we have developed a simple, flexible, multi-cube method for solving PDEs on manifolds with arbitrary spatial topology. For each new topology, you need to have a multi-cube representation of that topology. We now know how to compute that in an easy, automatic way from a simplex structure, and you can get those that other people have generated. You need to create a reference metric smooth enough to handle the continuity conditions that you want. C1 is the minimum you need to do Einstein's equations. We know how to do that in 2 dimensions, and I think we're on the way to doing it in 3 dimensions. We're not quite there. We think we know how to do it, just we haven't got the code to work. We've tested the method. There's a paper that solves a whole bunch of elliptic and hyperbolic type equations on several manifolds of this sort and showed that you can get nice numerical convergence. In order to do Einstein's equations, we ended up having to go to this covariant representation. I don't know if that's necessary. We tried very hard to do it without and failed. And then this sort of immediately made it work. So anyway, that's available that people can use. And we've tested them at least on this sort of simple non-physical but solution over many time scales, right? So this went for 1,000 M. 2 pi is 1 light crossing time. So this is like 160 light crossing times of the system. So that's stable for a very long time with very good accuracy and convergence properties of the sort you would expect from the spectral methods we were using. Anyway, that's all I have to say. I'm happy to answer questions.
Okay, we have plenty of time for questions. Yeah, we have a question. So your polynomial of PDE has to be mapped to the same metric in the other coordinates.
Well, remember this map is only operating on the boundary. So you take the boundary values of this guy and it maps to the boundary values of that guy. So if on the boundary this metric is a polynomial of something, then the one next door also will be. Yeah. Yeah, because we built these maps. They're nice linear maps because of the way, right, we just take these cubes, we make them, I mean, it's polynomials in the coordinates, right? And so the coordinates were set up, they have the nice same size, and you just do this rigid rotation to glue the, so if it's a polynomial in one, it's a polynomial in the other. No. No. And the thing that kills you is not the tangential directions, it's the normal directions that screw you up. And it doesn't touch those at all. Yeah. This is true. We tried cranking up the amplitude of this to something big, and so it doesn't crash, but it saturates at a fairly high level of constraint violation because, I mean, you're really violating the constraints when you go in and do this. And so it's only because this particular test non-physical problem was chosen to be in a regime that would be as nice as possible from an analytic point of view, just to see. I mean, as you know, with codes, usually the things that break are much more fundamental, and we wanted to make sure that those things were not broken. But in terms of sort of cranking this up to do something more interesting, it breaks. Unfortunately, we tried.
Yes, I wonder, again, we could specify the differentiable structure from the triangulation. And I wonder if different differentiable structures that you might get are equivalent.
Yes. So in one of our papers, there's an appendix that shows if you have two different C-infinity metrics that you use to define these Jacobians, is it true that the Jacobians that you get are the same? And the answer is yes. So the differentiable structure, how it defines continuity of things across boundaries is invariant under the structure of that metric.
And that uses that dimension 3?
We only proved it in dimension 3. I mean, that's where I come from the astrophysics side of things, so I don't think in 13 dimensions. So I don't immediately generalize everything to d dimensions. I suspect, I mean, the structure of that proof was not very dimension dependent, though. So I suspect that can be generalized if somebody wants to do it.
Okay, so let me ask one.
Okay.
So, I mean, there's the old textbook stuff about, you know, a manifold is a topological space with an atlas. And a lot of the stuff that you showed us today is sort of the flavor of, you know, somebody hands me a topological space and I work like hell to make an atlas. Is life any easier if someone, you know, hands you an atlas to begin with?
So, I mean, if we had found on the web some, you know, giant collection of atli, or whatever the plural of atlases is, I suspect we could have made it, it can be, now, to use this code, right, it's not expecting that. So okay, so say you have one of these atlases. If you could represent your, and we know how to build a smooth metric on something that has a C-infinity atlas, right? So in each domain, you just take a flat metric, you build a partition of unity, and you just add them all up. Okay, so that gives you a smooth global metric. So, and then if you have this smooth global metric and you project it onto my cubes and tell me what it is, I can use it. Okay, I could just read that in and use it. Okay, but the how do you go from your atlas into my cubes? I have right at this minute I don't know how to do that, but maybe we can figure it out over coffee if somebody wants to talk about it. But
okay, great. Well, let's see. All right, so I think we're out of time.
I think we're done.
Our speaker-
Thank you.